Hey guys, welcome back to week 3 of distance learning. I'm going to get right into it so I don't waste your time because you guys understand this format at this point. This week I'd like to talk about population ecology as a continuation of what we have been talking about. We've been talking about organisms' roles in their environment, their niches, and how that affects the overall population. Last week we actually looked at conducting studies to measure population sizes in nature. So what we're going to look at this week is trying to calculate and estimate certain population sizes, how they'll change, if they'll grow, if they'll decay based on a number of factors. That being said, it is a little bit mathy. It involves some math equations. I'm going to do my best to simplify it as best I can. I wouldn't like to, I'm not going to try and spend too much time on this unit for a variety of reasons, but mostly because I understand it'd be kind of confusing to do away from a school setting, and I'm not a math teacher, so I'm not sure that I can deliver it in the most effective way possible, but we're going to try it anyway. That being said, I'm going to be really lenient on this next couple days. Math is not my strong suit, and I'm sure that's the same way for a lot of you. And again, since I'm not specialized in this area, I'm not sure that I'm going to be able to be much help, but I'm going to do my best to explain it in a way that is nice and simple. So, population ecology. Population ecology is exactly what it sounds like. It is the study of how populations change over time in ecosystems. So how they grow, how they decay, if certain organisms are at critical levels where they could be endangered, if there are organisms that are overpopulating the area, when we talk about what we talked about with invasive species, so on and so forth. So it's basically what we've been talking about, but now we're going to get into more of the numbers. So first and foremost, we're going to talk about the method of measurement. This is going to be the bulk of today. Today's going to be mostly background because, again, since it's dependent on math, I kind of wanted to get the background out of the way first. That way tomorrow and Thursday we can just focus on the practice problems. And I'm going to do some with you tomorrow, and then maybe Thursday we'll do a little bit more independent stuff, but we'll get there. So first and foremost, how are we going to measure this? In math, there are a couple ways you can measure growth. First one is exponential growth. The rate is constantly going up. So eventually the number will reach infinity, and you'll have a lot of copies of whatever it is that's being made. This is depicted by a J-shaped curve, as you can see by this picture. So you start off with a little, and it grows slowly at first. Then over time, as you get more and more, you'll start to see bigger and bigger changes. The easiest way to describe it is like if you multiply everything by 2, if you square something, what squaring something is, raising it to that exponent. 2 times 2 is 4, not that much. 4 times 2 is 8, a little bit more, but still not a lot. 16, 32, 64, you can see how the numbers start increasing by bigger and bigger numbers over time. Over time, eventually you'll get to a number that's so big that it'll constantly reach infinity. If that doesn't make sense, that's fine, because that's not how we're going to be modeling population growth. As you can see, or hopefully you can start to think, as I was explaining that, you can start to see some problems with that when it comes to organisms. Organisms have limited resources and they can't grow forever. We talked about this already with invasive species and niches and endangered species and all that stuff. Clearly, there are not enough resources for everything to grow indefinitely. That's why we have issues with overpopulation, both in nature and also just with people. We can see how some areas are overpopulated, or if there are not enough resources to go around. You hear all the time people arguing about resource management. We don't have enough natural resources. We don't have enough fossil fuels. We don't have enough clean water. We don't have enough this, and this. And that's why. So we can't use this to model population growth. What we're going to be looking at instead is something you might not have heard of before. It's called logistic growth, and it's measured, or it's shown more of like an S-shaped curve, as you can see on this picture here. So this takes into account a variety of different factors. As you can see, it starts off looking very similar to population or exponential growth. However, it eventually reaches a number where it will not exceed a given point due to a variety of factors in place. If you remember from Bio 1, this is what we referred to as the carrying capacity. It is the maximum number of organisms that can fit in a certain ecosystem. That number can change. It can go up, it can go down, but it will always be there in some capacity. You will never have a population that does not have a carrying capacity, because that would imply that there's infinite resources, which is never the case. So we're going to learn how to measure that towards the end, but mostly tomorrow and Thursday. But I also want to get it out of the way and talk about what we're going to be looking for, and also things that impact it, so on and so forth. So we're going to be talking about carrying capacity today. I'm going to skim through this pretty quickly because this is a Bio 1 topic, and even if you don't remember that much from Bio 1, I think you can understand it pretty quickly. It's a pretty bare bones concept, and it's a lot of common sense kind of stuff. So anyway, carrying capacity, again, maximum number that a population can withhold. I always think of like an elevator or like a gymnasium or somewhere. If you ever see it posted, you'll see like maximum occupancy. You can only hold like this many people in this room or this elevator or whatever like that. So that's what I'm always thinking of when I think of that. So when allowed to grow uninhibited, organisms will eventually reach a state of equilibrium. Organisms are naturally adapted and evolved to always be seeking resources because in nature, unlike how we've kind of isolated ourselves and done a really good job of acquiring resources ourselves, in nature you don't know when you're going to be able to eat next or reproduce next or do the next thing because something is always constantly in your way or something's always constantly trying to kill you. So most organisms will take what they can get even if they don't need it. It's on a tangent, I'll try not to get too distracted, but if you're really curious, there's a lot of studies, interesting studies on like certain organisms that have like forethought, organisms that can plan for the future, whereas organisms that like consume everything in the moment. So like if they give them a food source that is more than they need, organisms that will eat it all right there even though they don't need to, versus organisms that'll save some for later. I'm getting off topic, but it's interesting to see which organisms are capable of forethought. I'll put a timestamp so you can skip that if you don't care about my ramblings. Anyway, lost my train of thought. Oh yeah, so organisms will take what they can get as long as they can get it. So again, assuming if there were infinite resources, that's why you would see exponential growth. However, clearly that's not the case. So organisms will usually grow to their carrying capacity when allowed to do so because there's no reason why they wouldn't. Anyway, factors that affect carrying capacity. Again, stuff we've talked about in Bio 1, but even if you don't remember, it's a lot of common sense kind of stuff. Available food, obviously that's a big one. You have to have enough food to support everybody. If you don't have enough food, then you're not going to have a population that's going to exceed the amount of food possible. Either people are going to have to leave, or people are going to have to die. Amount of space, you can only fit so many people into a given area. Obviously, if you have a room, let's say the size of my apartment's not going to fit 5,000 people in it. Somebody's going to have to go. Amount of water, predators, competition, all the basic things that you can think of. It's pretty self-explanatory. Important. I already mentioned this before. You can read this if you want. Oh, yeah, I'll skip this for now. Don't worry about it. Types of growth. There are 3 basic ways that an organism or a population can change. These are just to sum it down or summarize it very briefly. No matter what, they're usually going to fall into one of these 3 categories. Either they're going to be growing, they're going to be decaying, or they're going to be a state of equilibrium, which means they're not changing. Those are the only 3 states in which you can exist. So we're going to look at how we can measure that moving forward this week. So a really common example, and this will be on the website that I linked to, are predator-prey relationships. And we can see that based on this graph here. And I'll explain what this graph is depicting. Sorry, oh goodness. So in this graph, what you're seeing is the change in populations of the gazelles and lions over time. As the gazelle population increases, so does the lion population, because the lions eat the gazelles. The more gazelles there are, the more the lions can feed, the higher their carrying capacity. However, as the carrying capacity of the lions goes up, the carrying capacity of the gazelles goes down because the lions are hunting the gazelles. So then that decreases. When the population of gazelles goes down, so do the population of lions. And then you can see how that would fluctuate over time. This will happen a lot with predator-prey relationships. In some relationships like this, they kind of stable out and they will reach a point of equilibrium instead of constantly fluctuating. But this is just one example. Again, I'm trying to go fast. Let me know if you have questions. There's a thing. I'll get there. Competition is another one that would affect carrying capacity, as you would imagine. If I have a room to myself with 100 slices of pizza in it, I can have all those slices of pizza to myself, and that is the maximum number that I will get. However, if I'm sharing this room with 10 other people, I'm not going to probably get all 100 slices of those pizzas. Someone is going to outcompete me for at least one of those slices, probably more, because I don't eat that much. But anyway. Yeah, again, I'm skimming through a lot of this because this isn't the focus of what I want this week to be about. This is a lot of review stuff. So if you have any questions about this, let me know or pause the video and I'll also upload the PowerPoint, but I'm really skimming through this. Here's what I want to focus on this week. And here's where the math comes in, unfortunately. Before I go into this, first and foremost, I know this is going to be confusing. I'm going to do my best to explain it. We're not going to worry about it until tomorrow. And I'll do some practice problems with you in the video that I'm going to post for tomorrow, so you can see how it's done, and we'll see how this goes. I'm posting another resource or another link to Khan Academy. I found a section of this on Khan Academy, if you know what Khan Academy is, and they do a really good job of talking about all the stuff I've talked about today. They go into a lot more detail or stuff that I haven't covered yet, and I'm going to get into either tomorrow or Thursday. So if you're confused about anything, I would highly recommend you go to there. They have it laid out really well. The videos are very informative, if not a bit lengthy and redundant, but you can always skip through portions. And you can also click on whichever ones you want to look at the most. But anyway, For today, I just want to highlight the equation that we're going to look at and what the variables mean. So when you were calculating carrying capacity, which is what we're going to be doing for the rest of the week, looking at the maximum number of organisms that can live in a population, we're going to look at a couple of factors. One is population size, and this means the final population size. So how big is or dn is the final population size. So how big is it going to get? T is time, which I think is self-explanatory, but maybe it's not. So how much time are we looking at? And it's dependent on whether you're looking at months, days, years. It doesn't matter as long as you're consistent. If it says like this population has been growing for 10 days, what will it look like in this many years? You're going to have to convert. But if it's all within the same unit, then you can just use that. Carrying capacity is K, which you can represent here. And then R is the rate of change, which we're going to talk about more tomorrow and Thursday. We're going to talk about how to get that rate, how to look at that, how to measure that. It has to do with the amount of organisms being born. It has to do with the amount of organisms dying, coming in, coming out, a couple different factors, but it's pretty self-explanatory once you get the idea. Just basically like, are the number of births outnumbering the number of deaths? That will determine if your population is growing or decaying. And that will be shown whether this is a positive number or a negative number. So again, I'm not the best at explaining mathematical concepts. That's why I didn't go into math as a math teacher. However, unfortunately, biology does have a few mathematical representations in them due to how certain things are explained in biology. So I tend to avoid them, but sometimes they're unavoidable. I will do my best to explain it. That's why I've also posted other resources, because I acknowledge that I'm not the best at explaining these kinds of things. If you can't get it from me, hopefully you can get it from Khan Academy or somewhere else. Like I said, I'm going to be really lenient on this unit because I realize this is not everyone's strong suit. It's not my strong suit. And I realize I can only explain it so well. Even if we were in a classroom setting, we would still be kind of like on rocky shores. But now that we're at distance learning especially, I expect there to be a lot of confusion and a lot of issues. So do your best. Tomorrow's will most likely be participation because I'm expecting to do a lot of it with you, where I just do practice problems on the screen. And then we'll see how Thursday goes. We'll see what you guys are up to. But don't stress too much. One of the things on the Google form, the very last question is optional. If you have any questions before we go into the math tomorrow, I wanted to give you guys a chance to voice them, whether it's questions about any of this, like what these variables mean, it's questions about anything I presented earlier, anything like that. Feel free to answer it there. That way I can address them tomorrow. I'm kind of trying to preempt some issues we're going to have because I expect there to be a lot of questions and confusion during this unit. Maybe I'm wrong. Maybe I'm not giving you guys enough credit. Maybe this will be fine, but we'll see. I feel like I was going to say something else, but I forget what it was. But yeah, today's major focus is just kind of introducing this stuff so you guys are ready for the actual math tomorrow. The questions are just about concepts that I talked about here, concepts that I've linked on the Google Classroom, and then again, that question, or that thing at the end where if you have any questions, you can feel free to ask. I think that's it. So, we'll see how this goes. If I'm being honest, might end up scrapping a couple things if they don't work out right, but we'll see when we get there. Just hang in there for now. This should be a short section. I'm not expecting to spend too much time on this, and it's not crucial to our understanding of this overall unit, but it would be nice if we could incorporate this. So, anyway, have a good day. Talk to you guys tomorrow.